All right, this is answers to 2010. The average was almost a 6, so a little bit higher than the last rolling down incline with torque. Okay, so bowling ball, give you the mass, released from rest. They give you the length of the roof and the angle. Because it's a sphere, not a disk, it is 2/5 mr squared is the rotational inertia. And this should look familiar. Question A. On the figure below, draw and label the forces, not components, and draw them at the point of application. And this is worth 3 points. So again, if you watch the 1997 video, it's the exact same question. Everything has weight. You must draw that at the center of mass to get full credit. And I'm having trouble with my tablet, but it has weight. There's no fans. That's a normal force. It is touching a surface. That's the point of application. There are no ropes, but there is friction. And again, friction is tricky, but static friction is up the ramp because the nooks and crannies are trying to slide down the ramp, and what's happening is they're kind of rolling into the grooves and being caught and pulled up. So hopefully that's 3 free points. Question B, calculate the force due to friction. And that sounds on the surface really, really, really simple. Like, oh, F equals mu n. Why can't I just do that? So it's it's really tricky because it looks really simple, but they're giving you a hint. This is forces. You might need to refer back to your force diagram, so don't draw anything more. What I hope you will learn to see is this object is translating through space, so I'm going to need to do F equals ma. This object is rotating faster and faster and faster, so I'm going to need to do torque equals I alpha. And again, the reason I've spelled these problems out are they are really tricky, but once you see it, it's the same thing over and over again. So we're going to make 2 columns. Sum of the torque equals I alpha. And on some level, that one's easier because the normal force passes through the pivot, doesn't cause any torque. The weight is actually at the pivot, doesn't cause any torque. The only thing that causes torque is the force of friction. The lever, this is your pivot. The lever arm is there. So if you draw R and F from the same starting point, and then you go from R to F, that is positive 90 degrees. So we have, write your formula first, RF sine theta equals I, and I is sorry, they told you it's 2/5 mr squared. I don't think they give you R, but they give you M is 6 times alpha. And this little r is the same as big R. Okay, so that's R. We're looking for the force due to friction. So I actually made a mistake in my paper copy, and I plugged in mu n. We want F, so let's leave that as F. But what is tricky is that this is not the sine of 30 degrees. This is the angle between R and F, and we just figured out that was 90. So this is sine of 90, which is 1, equals 12/5 R squared alpha. So yay, 1R cancels. So you might say, and sine of 90 is 1. So F is 12/5 fifths are alpha. But it's not in terms of other, it's not a number. So we're not done. So we're like, well, shoot, what do we do now? Okay, well, that same object is both translating and rotating. So let's do sum of the forces equals MA. And that's trickier because it's accelerating parallel to the ramp. So the normal force, not a factor-ish because it's perpendicular. So remember that when something's going down an incline, you have mg sine theta that makes it slide. That's parallel to the incline, so that's going to matter. And you have, what color can I use? This one here is mg cosine theta that makes contact. So the normal force is equal to mg cosine theta. We may or may not need that, but what's important is we want all of the forces that are parallel to that are affecting the linear acceleration. So that means mg sine, highlight that, that means friction. So that's how we're going to get rid of some of those unknowns. It's because there's more information about friction hidden in that force diagram. Okay, so we did sum of the torque equals I alpha, check. Now we're going to do sigma F equals MA. So you have mg sine theta makes it slide. This is the theta that's labeled 30 degrees minus the force of friction. Oh, I'm making a capital F because that was effort anyway, whatever. Equals MA. And we are looking for F. So we don't want to solve this for F and set them equal because that'll get rid of F. But A equals alpha R. So I suggest we plug that in. And so we have mg sine of 30, which is a half, I'm pretty sure. Yeah, so we have mg, and we know m is 6. So this is sine of 30. Hopefully that makes sense. This is sine of 90 because it's definition of torque. This is sine of 30 because we're breaking down the mg, and that had to do with the incline, not with torque. Okay, minus F equals M, which we know, but I'm trying not to plug numbers in, alpha times R. Okay, yay, then the mass cancels. Nope, no, it doesn't. Sorry. Alpha is mg over 2 minus F all over mr equals alpha. And let's plug that in over here. This may not be the most elegant way to do it, but it is, again, sometimes there's no one linear way to do it. Let's plug that in for alpha. So m is actually 6. I don't know if we want to, let's turn this into two different fractions. So we have mg over 2mr, and now my m's will cancel, minus F over mr. Okay, so m can go away even though we know what it is. So F equals 12/5 r. Oh, look at that. The r's are going to cancel too. Okay, so it equals 12/5 times g over 2 minus F over m, and that m didn't cancel, so that's 6. Okay, so F equals 6/5 g, that's just a number, minus, let's see, 2F over 5, right? Because 6 goes into 12 twice. And now let's add 2/5 F's to both sides. So F plus 2/5 F's equals 6/5 G. I like that there's a bunch of 5s in the denominator. And then this is 5/5. So 7/5 F equals 6/5 G. The 5s go away. So F, the friction, equals 6/7 G. Which is, I have no idea if I'm right. 6 divided by 7 times 9 equals 8.4 newtons. So that's not the coefficient. So that's okay that it's bigger than 1. 8.4 newtons. All right, let me check. Sorry, it's moving things around there. 8.4 newtons. Whew. I was correct. Again, that may not have been the most elegant way to do it. So, but like I said, like if it does look too easy, then it can be frustrating. You can just see that we're just, you might have solved for something different first. You might have found an easier way to combine information. Okay, but the answer is 8.4 newtons. Okay, then question C says, find the linear speed of the center of mass when it reaches the bottom edge of the roof. So linear speed is v. You have two options. The object is going from point A to point B, and we want the speed. So to me, the easiest way to do this is energy. So in my paper answers, I kind of work things through more complicated. I solved for A in order to get F. So you can look at my paper answers. I solved for A and then use don't know, don't care to find the linear speed. But in this case, we didn't solve for A. So I think the easiest thing to do is to say T me at A equals T me at B. Again, the AP graders are going to give you credit no matter how you do it, as long as it's legit. So you can look at the paper answers for if you wanted to go back and go, okay, F equals MA, I'm so close to finding A, and then use don't know, don't care. But let's practice using energy. So at the top of the incline, it only has MGH. At the bottom of the incline, it is translating through space, and that's what we're looking for. And some of the energy is cost you rotating. The mass is, the mass is going to cancel, so I'm not going to put the mass in. But the height, you got to be careful. The height is not 4. The height is this, which is for stop sign, for sine of 30, or 2 meters. Okay, so your vector breakdown is important. So this is m times g times 2 meters plus 1/2, equals. Again, we know that m is 6, but I know it's going to go away too. Equals v squared, that's what we want, plus 1/2. I, they told you, was 2/5, I believe, 2/5 mr squared. And omega equals v over r because of no slip. So v equals omega r, so I just solved that for omega. And again, I deliberately didn't want to put the mass in because I knew it was going to save us some time. That's going to cancel. These r's are going to cancel. So we have 2 times 9.8 equals v squared over 2 plus, the 2's cancel, v squared over 5. So the common denominator is going to be 10. 2g equals 5v squared over 10 plus 2v squared over 10, 7v squared over 10. So v squared equals 2g times 10 over 7. All right, so v squared multiplying all that out is 28. And then take the square root of that, and the speed is 5.29 meters per second. Whew. Okay, and then if you go back and look at the picture, because the AP is cumulative, the reason they had you find the linear speed is that is now 5.29, and then this becomes a projectile. So we're going to quickly go down and look at that. A wagon containing a box, it falls and then lands and sticks. This is a collision in the center of the box. Calculate the horizontal speed of the wagon after the box lands in it. All right, so this is deceptively, not necessarily super tricky, but it's really two separate problems, and people might have just gone straight to the collision, forgetting that something happened between, I'm going to say, point B and point C. It fell 3 meters. So it is now a projectile. And so there's a couple of hidden concepts in here. So the speed right here is 5.29. I'm going to draw this up here. It is ejected with a speed of 5.29, and some of that speed is, or hopefully it makes sense, that this is also 30 degrees by alternate interior angles. So this speed is 5.29 cosine of 30, because the angle that you know is closer to that leg. And we have 5.29 sine of 30. And Okay, actually, this 3 meters is kind of irrelevant, because as it falls, the force on it is only gravity. So that is not going to affect the horizontal speed. Go back and review the projectile unit, everything, or just remember Newton's first law, that horizontal speed is constant. So that vertical speed is getting longer and longer and longer. So as it impacts the wagon, it still has a horizontal speed of 4.58. That doesn't change. So it's still going over at 4.58. Sorry, my fours get messed up. The vertical speed has gotten bigger because gravity is pulling it down faster and faster and faster. But that doesn't matter, because the vertical speed is going to hit the floor of the wagon. That's going to cause a normal reactive force, and that's going to cause an impulse. That's an outside force. The floor is going to push up. So momentum isn't conserved vertically. It's going to come to rest. It's going to lose all of that. We didn't care about that. And then we're going to have a collision with just the horizontal speed. So I'll go down and draw this. So we have just the horizontal speed of the wagon, 4.58. And if you remember, this was a problem. I know it was one problem a long time ago, but there was a piece of coal coming out of a chute. That's one of the reasons why I assigned that momentum question. Okay, so the wagon is 12 kilograms and it's at rest. And so the 3 meters is completely irrelevant. But I need to know the mass. Oh, 6 kilograms. Okay, so we have 6 kilograms moving forward at 4.58. This is our before picture. And it collides with the wagon. Our after picture is an 18 kilogram combined thing with an unknown final speed. All right, hopefully that makes sense. We got to isolate the horizontal and vertical, and so we're only dealing with the horizontal momentum in our before and after. The vertical momentum is not conserved because the floor is an outside force. Okay, so then once you realize that, it's a pretty straightforward momentum problem. Sum of the initial momentum equals sum of the final momentum. So we have mv plus 0 equals m tote v final. So we have 6 kilograms times 4.58 equals 18 kilograms times V final. And then since 18 is 3 times 6, the V final is going to be 4.58 meters per second divided by 3, or 1.53 meters per second. And how many points is that worth? That was worth 3 points. So the tricky thing was to realize that that 3 meters was completely irrelevant, but you did have to find only the horizontal component of the speed of the ball. The AP is really nice about error carried forward. So if you had the wrong linear speed in C, but move forward with that in D, you would have gotten all 3 points in D. Okay. Hopefully that is going well. And you can see both of the solutions are over 15 minutes, which is what we used to have for the long answer. So it really is a time rush, but it's, in my opinion, better to do the problems thoughtfully. As long as you're working, you're getting points in theory, as long as you're working and doing good work. Then I would say that is better than trying to rush through and then make careless mistakes, like using all of the speed instead of just the horizontal speed. Okay. Hopefully that's making sense. Please reach out if you have any questions.